This is our presentation for ECE 532. Today we're discussing how to develop an autonomous driving assistance system using systems engineering and sensor fusion. So starting off with an introduction, there are two main pieces that come into play while creating an autonomous system: the hardware end and the software end. So in regards to the hardware end, we'll have components like the radar, LiDAR, and/or camera vision sensor. And this hardware is essentially in play to pick up information from the surroundings. Kind of like how if we're driving along, we're looking around, hopefully not looking at our phones, but looking on the road and seeing what's out there, if there's anything of importance, scanning pretty much everything, seeing cars on the road, for example. So that would be the hardware end. And then in order to translate that information into usable information for the vehicle and computers, we'll have software, which coupling that hardware and that software end, which allows the vehicle to pretty much work in a way as a human normally would. We'd have sensor fusion that couples all that information together. Moving on to some hardware used and autonomous driving vehicle levels. So in terms of cost, some of the information I mentioned earlier for hardware, the radar normally comes out as the cheapest. It's been around the longest for assisted driving. That would come into play. I believe in 2007 was the first, 2006 or 2007 was the first vehicle that was created with radar that could be used for, say, for example, just having an automated cruise control, which would be able to detect the vehicle out in front and determine what speed the vehicle should travel at. Well, our vehicle, say for example, would travel at compared to the vehicle out in front. But that is the cheapest. Then camera, as we can see, the range is a bit on the, can go up to the higher end. And LiDAR is fairly expensive compared to radar and camera. So below that table, I included another table with the advantages and, well, an advantage and a disadvantage of each, the camera, LiDAR, and radar. So the biggest advantage of camera is vision. It works extremely similar to a human eye. Disadvantage would be poor vision under bad weather, similar to how it would be more difficult for us to drive under, say, like heavy rain or heavy snowfall, at least here in Michigan. In terms of LiDAR, it's excellent in weather and has great vision. So any extreme weather you could have, it works much better than camera normally would. But the downside is the high cost. As you can see from the table above, it's definitely not cheap. This was a price from Google back in 2008 if you wanted to purchase their Waymo camera system. And then in regards to radar, it's great in weather conditions, but the models that it'll produce are low definition. It just can't compete with camera and LiDAR. I guess a good pro based on that low definition would be it wouldn't require as much computing power, whereas with camera and LiDAR, you'd require a lot more computing power simply because you're getting more information in a shorter period of time, compiling it all together. So in regards to the levels of driving automation, we have 6 levels in total, 5 of which are actual autonomous driving levels where you actually have a system in place, or at least part of some system. So starting off at level 0, this is just the conventional level you'd think of any car that doesn't have any type of driver assistance. This can be like a, say for example, like a 2000 Chevy Impala. Mostly, I'd say just about every car before 2006. Moving on to level 1, this will be just basic feature that vehicle might have, like let's say lane collision, not lane collision, lane centering, or maybe detection of the vehicle out in front with cruise. And then we'd have partial automation in level 2. This would be considered most of the vehicles that you would consider the highest end of autonomy today. Say, vehicles with the GM Super Cruise or Tesla's autopilot feature. Even though there has been some confusion with autopilot and some users assume that it would be higher up, this feature would be more along the lines of, it would be level 2 autonomy, even though they consider it 2+, stated by the automakers sometimes. Level 3 would be considered a bit of a gray area for automakers, since a driver would have to still be attentive on the road, but some of the capabilities are possibly considered on level 4, since the vehicle can perform most of the driving tasks. This level 3 system will most likely not be included when automakers release vehicles, but that is still to be seen, and if that would be made. Automakers would most likely jump from 2, or what they consider 2+, up to level 4, just for safety on just regulations and liability. Level 4 would be, this would be when human interaction would not really be needed. It would be advised that the human is still in control, but the vehicle should be able to perform most tasks. And then moving on to level 5, the vehicle should be able to work on and perform all tasks while moving. And this is still, say, mostly an imaginary state. We still, in terms of systems engineering, this hasn't really been able to have been proved or been possible yet, but with years of work into the future, this can be a possibility, and it can save pretty much, you could say, like over 90%, assuming over 90% of crashes that are on the road today. And since driver-related accidents are high, this can be very helpful for just saving lives in general. Moving on to the safety standards. So safety standards are not a requirement, but they're put in place for best practices, just to develop a vehicle in the most, say, efficient way, but also in terms of following the correct procedures to not have any recalls down the road or any defects of major defects that could lead to any catastrophic events within the vehicle. So on the left, we have the ASPICE compliance. In the center, we have ISO 26262. And on the right, we have SAE J3016. These are considered some of the automotive safety practices that are most common within the industry that are followed for autonomous driving vehicles. Moving on to systems engineering and the V model. Systems engineering plays a crucial role in the development of the vehicle. It will normally follow some of the safety standards that were mentioned in the previous slide. And the V model is an excellent portrayal of how a process is followed in order to create a system safe for autonomous driving vehicles in the future. And these projects are multi-year, which means each step in the process should be followed in order to create the correct vehicle and follow all the steps required. So starting off on the top left, we have the requirement analysis and functional specifications. Within this section, we're essentially defining what the vehicle is going to do within documentation and requirements. So in this case, we could say if the vehicle must keep at least 5 feet away from the other vehicle at all times while driving at, say, 50 miles an hour, that would be something that would be reported in the requirement analysis and functional specification. It's reported here in order to document it for the work that will be going on later on down the road in regards to the sensor fusion and any programming that would be involved, just so that's documented during the programming phase. The programming phase would be lower on in the V model. This can be, let's say, like after the high-level design, the detailed design and program specifications will allow it. Well, this will be the section where programming will start to be implemented, and the requirements. Individuals that created the requirements will communicate to the individuals that are creating the programming in order to have correct code implemented. And once the correct code is implemented, then the hardware and software will both be tested through simulations in order to verify that the say hardware will be just able to work properly. And then this is where you'll have testing such as like the hardware in loop, processor in loop, testing out your autonomous driving, pretty much anything that goes along with the autonomous driving. And along with that, in this case, we'd have just any like validation, but the actual physical testing won't take place until later. This is mainly due to cost perspective, because now that the hardware is being tested along with the software, you can catch bugs and just go back to the drawing table and recreate code or revise code that may need any revisions. Once any bugs have been sorted out, then the recommendation would be to move on to the systems testing and user acceptance testing. So in the systems testing, this will be when the hardware and software will be tested, but in the real world. This unit testing will allow drivers to see pretty much everything and just see if it actually works, how it worked in the simulation. Once that is completed, the user acceptance testing will be a phase where pretty much any users, this can be everyday individuals, are able to test out the vehicle and just use it how they normally would and look for any bugs. In this case, just having a lot of individuals testing vehicles will be acceptable, since you'd have a high amount of people instead of just one or two. If you think about like a lower end statistic of people testing it. And that would be the role of the V model coupled with systems engineering. Moving on to software and sensor fusion.
Thank you, Innis, for your presentation. Now I'm taking on to talk about sensor fusion for autonomous driving, and especially the algorithmic side. So in the beginning, I want to talk about the features, the different types of algorithms that are used to do this task. So from one side, we have classical algorithms. Here we may have traditional algorithms and also deep learning based algorithms. So for the traditional algorithms, what we have are two steps. First step is feature engineering or the feature extraction. Here we will be using handcrafted features, and mainly these will be extracted using some mathematical operations, stuff like that, and many types of them exist. We can mainly name SIFT and FAST as feature extractors. Then the step is followed by a classifier. So while this classifier can be a neural network, it can also be any machine learning classification algorithm, so such as an SVM, multi-layer perceptron, and anything of the source. And then we will have our output. For deep learning algorithm, what we can see here is that the feature learning task is actually automated. So basically, the algorithm will try by itself to learn what are the features that are most relevant to the detection or to do whatever task that you want to do, and then this is followed by a classifier. And this classifier will usually be a shallow, dense neural network. And for feature learning, we most commonly use convolutional neural networks that do convolution operations either in 2D space or in 3D space. In our work, we will focus mainly on deep learning based algorithms, as these represent right now the state of the art for the problem of tracking and detection that we want to address. So let's talk about how sensor fusion is performed for a deep learning application. So basically, sensor fusion can happen in 3 different stages of decision making, and sometimes algorithms will implement it in just a single stage, or it can be implemented in all of them. And this depends on the choice of the researcher working on it. So sometimes input can be combined from multiple sensors and on the raw data level. So in this case, it can be projecting projecting a point cloud on a 2D plane, or stitching together multiple images to form from multiple cameras to form one giant image. On the feature extraction level, this mostly happens after the initial convolution layers, and basically like every sensor will feed off its output into a feature extractor algorithm, and then the most relevant features will be combined together, either using a special fusion module, or in some other cases by just concatenating the features together to form one giant feature set. Finally, it can happen on decision level, where you do whatever operation you want independently using both sensors, and then combine the result at the end. So you'll be having here multiple neural networks corresponding to multiple sensors running in parallel, and then they can either like vote for whatever classification task that you want to have, or if it's a regression problem, you can average out their outputs, and correspondingly have a final decision made by the ensemble of models. So to evaluate deep learning algorithms that are working on abstract tasks, we have chosen as a benchmark the Getty dataset. So this dataset was created by scientists from the Research Institute and the Karlsruhe Institute of Technology in Germany, and it has grown since then to include scientists from all over the world and from multiple other research institutes. So the vehicle that is used to collect the data from the dataset is standard across all benchmarks. It has a stereo camera that is capable of capturing 100 color images, LiDAR, which is highlighted in green, and a GPS for data collection. So, owing to the exhaustiveness of the dataset, we selected decided to follow the tracking and detection benchmark, since it is one of the most active and challenged and developed benchmarks around. And in our selection, we have decided to select papers of the selected approaches that have publicly available papers. So even if an approach has state-of-the-art performance and it doesn't have a published paper, we will not want included in our literature review. Also, the approach must use sensor fusion, and thus we have into choosing only 5 approaches, and we will present next. So the first approach is called AutoTrack, and it was proposed by researchers from the University of Toronto, and this approach is all about creating a very fast, lightweight detection and tracking algorithm. So to do this, they are using images from 2D cameras and LiDAR. Then what they are doing is that they're taking the 2D image, and then performing 2D detection on it. Afterwards, they project the LiDAR point cloud data onto the 2D image. Finally, they cluster all the point cloud points that they have to create some form of 3D centroids, and then that they use they feed to a tracker, that is a Kalman filter that performs the tracking in 3D space. And here you can see the projected image and the projected point clouds onto the image. So this approach's focus is on robustness and on redundancy, even in case that we don't have way too many sensors, or if a sensor malfunctions. So the pipeline for this approach has 4 major blocks. The first block is the detection, followed by the feature extraction, adjacency estimation, and then the optimization. So for the detection, the algorithm starts by using a detector for the image, and either in 2D or in 3D, and then it uses VG16 as a feature extractor or PointNet as a feature extractor. Then once they have the feature vectors, these are combined using a fusion module. So essentially this fusion module gives off essentially the output here is 3 sets of features: 2D features, 3D features, and fused features. And this fusion is done in order to enhance the correlation between the images and to improve redundancy in case one image has incomplete information, or if it was included, etc. So this here is one of the most difficult parts that they have performed, and essentially it's the adjacency estimation. So the authors here are looking onto each car as if it was its very own object that is moving in a graph. So, and the way they're looking at it is that they model the world and the tracks that the vehicles are going to in the form of graphs, and then they try to determine which node the vehicle will travel to. And in order to do this, they have 4 components. So this big block here is a correlation component, which aggregates all the features that come from the fusion module, from the 2D feature extraction, and from 3D feature extraction. This is followed by the start and end estimator. So this one will try to tell whether the vehicle has entered the frame or left it, and the confidence estimator will try to find out what is the degree of confidence that we're doing in this whole prediction. And the affinity estimator is the one that is trying to find where the vehicle is going to be next on the graph. So even after we have this whole operation, all these variables are then optimized using linear programming into binary variables in binary matrices, while the probabilities are then translated and optimized using this heuristic into something a bit more deterministic, and that's how we get the final result. So eagermod is another algorithm that proposes a greedy approach to the problem. So basically we have a 2D detector and a 3D detector. So using images coming from lidars and regular images from cameras. These both will then will then be combined into a singular image that has a 3D bounding box but in the 2D space. So after doing this, the algorithm will try to greedily match the fusion result in so this fusion result that we have here in the 2D space that is combined, it tries to greedily match it in the 3D space and in the 2D space. And basically the matching in the 3D space is actually only used to enhance the process of tracking that is happening here. So for this process of tracking, the authors use a Kalman filter in order to predict the states and initialize and terminate whatever tracks they have to follow the vehicles. Then using this, they update the tracks to find out where the vehicles will be going and where every vehicle is going to be, and then they use this data to enhance the next form of 3D data association that will enhance the next form of data association in 2D space, and the virtuous cycle continue. And their strong point here is that they're leveraging previous information in order to enhance their current predictions. So the GMOT paper is actually pretty unique, even because it works on doing the detection and the tracking simultaneously in a single block. So the way we get this is that it uses autoencoders in order to layer the bounding boxes on the images, and then what it does is that it combines these newly created point cloud data and images with the pointwise feature fusion, and afterwards these regions of interest where we have the detected vehicles or seemingly detected vehicles are passed into an object detection network and an object correlation network. So the object detection network will classify the object, so detect if it's a car, if it's a pedestrian, and the box regression network will try to find out where this box is moving and where it has come from, and information like this. And the object correlation network has a re-identification module that's going to try to find out if a vehicle detected is a vehicle that the network has already seen, or if it's a new vehicle, and a start and end estimation that will try to say if this is a newly detected vehicle or if a vehicle has left its track and is out of the field of view of our car. So the re-identification process works by greedily matching all the proposed regions with the features that we have and giving out multiple scores. Then these scores are going to be ranked, and simply here the motion prediction information will be used to finally compute the affinity of every vehicle that has been detected. And by affinity we mean that if we mean that we will finally find out which vehicle in frame T in frame T corresponds to any previous detection. So the whole process afterwards is optimized using mixed integer programming, which is a kind of dynamic programming to finally give us the tracking information, whether we have a new track that's being birthed, whether we are missing whether a vehicle is missing, if it is partially occluded, and then if a track dies. So GRMod has the objective of being a real-time framework for 3D multi-objective tracking. And it works by using the detection and then tracking paradigm. So what it does is that it has an input from the LiDAR and from the camera. It initially starts with doing its detection on the input from the camera onto the image. Since 2D detectors are more precise than 3D detectors, then it leverages the results of the detection to create with the point cloud image to essentially do the detection in the 3D space and then find out an appearance model. And also it uses this to determine the 2D appearance model for the detected object. Then the results are combined using feature fusion, which is a multi-layer perceptron that determines which features are being used, the features that are being fused, and the result of the 2D detection is then used and associated with the fused features, and the result of a Kalman filter that will try to estimate where the vehicle is at instant t. And all of these are used using a gating and cost selection method that tries to find out the intersection over union of the fused features in the space with the detections that we have, and then all of this use a joint probabilistic algorithm, and the final results are filtered through a multi-model Kalman filter, which will then be updated and will be able to determine the exact position of the vehicle at instant t, or not the exact, but try to determine the position of the vehicle at instant. So to evaluate the approaches that we have encountered, Kitty is using the HADA metric, and this metric measures the veracity of the cumulative average alignment of matching detections while castigating those that don't align. So HADA has three subcomponents. Log A, which measures the localization accuracy, det A, and it measures the detection accuracy, and SA, that measures the association accuracy. So for the results of the comparison for the five approaches that we're talking about, we'll find that the best performing approach was ERMOD with a HODA of 74.39% and a localization accuracy of 87.17%. So we find that for the detection part, it slightly edges out over all the other contestants with 75.27%, but for the association part, it is actually significantly better than the others with a score of 74.16%. Another one of the contestants that we can talk about is actually GRMod. So while GRMod doesn't have HODA, it is as high as the others. One of its main attributes is that is running almost real time, and for this compromises offered and the increase of speed, its auto is 69.61%. So while you are sacrificing performance and accuracy, you are gaining more on processing time and maybe feeling in the constraints of a computationally less powerful system. And another mention is Gmod, that offers slightly higher performance than grmod, while also offering better robustness. So in case of if there is a failure of one of the sensors or a cybersecurity attack, Gmod is the one that is designed with these scenarios in mind, and in order to offer better robustness than